We learned earlier that the factors of a polynomial function may be used to determine the zeros and therefore the x-intercepts of the graph of the function. Now let's review what the expanded form of a polynomial function tells us about the shape of the graph.
The degree of a polynomial function is represented by the exponent on the term with the highest numbered exponent. If the degree of the function is odd and the coefficient of the term highest degree is positive, then the graph of the function will rise from left to right. If the coefficient of the term of highest degree is negative, then the graph of the function will fall from left to right. If the degree of a polynomial is even and the coefficient of the highest degree term is positive, then the graph of the function falls from the far left and rises to the far right. A negative coefficient causes the graph to rise from the far left and to fall to the far right. The zeros of a polynomial function correspond to the x-intercepts of its graph. There may be 0, 1, 2, or more x-intercepts, depending on the function. There is always one y-intercept, and it is equal to the constant term of the function. If there is no constant term, the y-intercept is 0.
When I study for tests, I like to review my old quizzes and assignments. When I get them back originally, I highlight the things I'm having problems with. That way, I can focus on those areas to make sure I understand them.
When we're given a polynomial function, we can analyze it and sketch the graph. We're also able to use the graph to determine the unique function it represents. This is the graph of a cubic polynomial function. From the graph, we can see that the x-intercepts are -4, -1, and +2. And therefore, the factors of this polynomial function must be x plus 4, x plus 1, and x minus 2. Notice that each factor occurs only once because the graph goes directly through each point. Each zero has multiplicity 1. However, to determine the exact or unique equation of the polynomial function represented by the graph, some more information is needed. The polynomial function could be written as y equals k times x plus 4 times x plus 1 times x minus 2, where k is some constant. It is this value k that makes the function unique. To find k, we need to know another point in the graph. From the graph, we see that the y-intercept is 16. This point then has coordinates 0, 16. If we substitute 16 in for the value of the function y, when x is equal to 0, we obtain 16 equals k times 0 plus 4 times 0 plus 1 times 0 minus 2. Simplifying, 16 equals -8k, and therefore k must be equal to -2. We now have found the unique equation represented by this graph. Y equals -2 times x plus 4 times x plus 1 times x minus 2, or in the expanded form, y equals -2x cubed minus 6x squared plus 12x plus 16. Note that it required 4 points to determine the exact equation of this polynomial function. Polynomial functions which have only real zeros require the zeros and their multiplicities, along with a point on the function that is off the x-axis to uniquely define their equation.
Whenever I write a test, and there's a question with a graph, I make sure that I look at the scale of the x and y axes, as well as some specific points like x and y intercepts. I feel that somehow this information might help me when I'm finding my solution.
We're going to use this graph to help us next some concepts. By now in your studies, you should be able to look at a graph and describe its distinguishing features. For example, you should be able to look at this graph and tell me the degree of the function is 4. In other words, the quartic function is opening upwards. The leading coefficient then must be positive. You should also be able to recognize that there are 4 zeros of the function, that we have a 0 of -2 with a multiplicity of 1, another of +3 also with a multiplicity of 1, and that we have 2 equal zeros of 1/2. Or in other words, we have a 0 of 1/2 the multiplicity of 2. And we can tell this because there is a touch at 1/2. We know then that the factors of the function are x plus 2. This we know because p at negative 2 is equal to 0. Factor theorem therefore says that x plus 2 is a factor. We also know then that x minus 3 is a factor, and x minus 1/2 squared is also 2 of the factors of the function. We can also see that the y-intercept of the function is negative 12. In other words, the function passes through the point 0, negative 12. If we were asked to find the exact equation for the integral polynomial function, what we would need to do is write f at x is equal to a, some constant factor multiplied by our factors, x plus 2, x minus 3, and rather than writing x minus 1/2 squared, I'm going to write 2x minus 1 squared so that I don't have to deal with the fractions. Now, we want to find a unique function. We need to find the value of a. We're going to use the other information given in our graph that the y-intercept is negative 12. A common mistake is for students just to dash a negative 12 down at the end, thinking that that's the constant term. This is not how you handle that information. What you do with that negative 12 is use the knowledge that when x is 0, f at x is equal to negative 12, and substitute those values in. We get then negative 12 is equal to a multiplied by 2, multiplied by negative 3, multiplied by 2 times 0, minus 1 squared. Solving now for a, we get negative 12 is equal to negative 6a. A, therefore, is equal to positive 2. And although now we found the constant factor, we still need to substitute that back into the function in order to write the exact unique function that we're looking for. The function, therefore, is equal to 2 times x plus 2 times x minus 3 times 2x minus 1 squared. We could verify that function by substituting in any one of our 3 zeros. We could substitute in negative 2 in for x, and we should get 0, or 1/2, or 3. We could also graph the function on our graphing calculator and verify that it does in fact look like the given graph, or we could expand the function in order to check that the constant term is in fact negative 12. Although I've chosen this path to find the function that the graph represents, there are other paths that would have led you to the same function.